Alright, so we're starting off our discussion of Lie groups today. Kind of, not really, because we're going to be doing a lot more setup for this than we did for Lie algebras. Like for algebras, we just kind of went over what an algebra is. We looked at the properties of the extra properties that make it a Lie algebra, and then you kind of just go into it. We're going to do a lot more, because the Lie group, I kind of vaguely alluded to, it needs to be on a differentiable manifold. So we need a lot more setup to kind of get to what that is particularly and how it ties to a Lie algebra. So our first chapter here is going to be on complete fields. Alright, and to start out the definition, let K be a commutative and absolute value is on K is defined to be a function from K to the positive real numbers, which we of course denoted, we denote with the standard absolute value symbol, such that the first condition, an element has an absolute value of 0 if and only if it is 0. So if you recall, an absolute value kind of measures the size of a number, and so 0 is the only number with the size of 0. Number 2 says that this behaves well with products. The product of the size is the size of the products. Number 3 is that our multiplicative unit has a size of 1. This isn't unique like 0 is, because for example, our normal a normal absolute value on the real numbers will have also -1. In the complex numbers, the unit circle will have an absolute value of 1, but still. And our final condition is the triangle inequality, where x, the size of the sum is at most the sum of the sizes. I need to orient my phone a little differently here. And so there's 3 standard examples we look at when we talk about absolute values. The first one is we take the absolute value of x to be, I'm going to write it in a weird way, like this. So essentially what this is, if x is 0, then this delta is going to be 1, so this is going to value to be 0. If x is not 0, this is going to be 1. The topology induced by this absolute value is discrete. This is the trivial absolute value. And it says from now on we will assume that the absolute value is non-trivial so namely there exists an element k whose absolute value is between 0 and 1 and not 0 or 1. Our second example of an absolute value is the reals and the complex numbers with the standard absolute value. The third one isn't actually an example. I guess I'll write it as an example. We sometimes replace our fourth condition with an alternative fourth condition, which just states that the size of the difference of two vectors is at most the size of the larger one. This gives us what we call an ultrametric or alternatively non-Archimedean absolute value. And these are used for, these construct our p-adics and that kind of thing. Note that this condition is equivalent to saying that for epsilon being non-negative, it can be 0 in this case. Sorry, 1 second. It's saying that essentially everything kind of curls up into localized balls. So that's saying that taking groups of items which are all within epsilon of each other is an equivalence relation. And so the way this is kind of weird to think about, essentially what it says, if we have an epsilon, if you have an item x and y, which are epsilon apart, at most epsilon apart, and a third that's element z that's at most epsilon apart from one of them, then it's going to be at most epsilon away from everything else in here, and more than epsilon away from everything outside. And so you can, the whole space kind of, like for the p-adics, you usually see this picture of like, this is the whole integer, all the p-adic integers, and then this next smallest value, you get like 3 different groups of them, and then they each have like different equivalence classes inside them for a smaller size, and it just keeps kind of recurring inside of itself in this kind of fractal structure. Now, we want to suppose K is complete for such an ultrametric absolute value. And this brings us to our an immediate theorem. We let xn be a sequence with each xn in our field K. Then their sum converges. It converges as a sum if and only if they go 0 as a sequence. And this is just automatic from this alternative definition above. Now we come to another theorem. This is Ostrowski's theorem. And this is what I was alluding to earlier, where like these three examples of the trivial, the standard on real complex, and this ultrametric are kind of the three cases you look at normally, and this is why. So we're going to let K be a complete field for an absolute value. And in this context, I'm pretty sure that just means that every Cauchy sequence converges to a point in the space. So maybe just every sequence, every typical convergent sequence. Then there's actually three cases. The first is that the absolute value is trivial, which we discounted before. We just said we're not going to deal with that. The second is that K is either the reals or the complex numbers with the usual absolute value, which we call the absolute value of x to the alpha, for alpha being positive and at most 1, or the absolute value is an ultrametric. The proof of this is not worth it for what we're aiming for. You can find it on Wikipedia, you can find it in lots of books. You just look up like Ostrowski's theorem. I think Wikipedia goes through the proof. But you can, right now we don't need to worry ourselves with that. Now we're going to let K again be a field with an ultrametric absolute value, say like that. And let A be a real number between 0 and 1. Define a real number well, A is going to be real, of course. But a real number v of x by the formula the absolute value of x is equal to a to the power of v of x. Then Vx satisfies well, first off, v of x is positive infinity, so I guess it's kind of on the extended reals. If and only if x is 0. Second is that v of x times y is v of x plus v of y. That's kind of our standard product rule. Our third condition is that v of 1 is equal to 0. And our fourth condition, v of x plus y, is at least the smaller of v of x and vy. And with this, v of x is called the evaluation of x. And this is kind of hard to a bit kind of esoteric, a bit, I don't know what the right word is. Dense is the one that keeps coming to me. Opaque. So let's look at some examples. Part A, we're going to let k be the way the rating at C, that's supposed to be, yeah, that's the complex numbers. It's going to be the formal power series. I gotta figure out how I'm going to write this. The formal power series on the complex numbers and then just a single determinant t. I'm going to let A be the sum of n. They have double greater than negative infinity of a to the n times t to the n with a to the n with each a to the n complex and an equals 0 for large negative n. We're going to define a valuation of a to be the smallest n such that that coefficient is non-zero. Then we have that a is Tn times a0 plus a1t. So I'll just write it like this: a to the I, t to the a to the a sub j times t to the j for j from 0 to infinity, with a 0, non-zero, n an integer, so once again I'm going to have to reorient myself here. That is, saying that v of a is at least n is saying that a is equal to t to the n phi, with phi being an element of C over one of these is the formal Laurent series. Note that the field CT, yeah, I think the curved brackets is supposed to be, oh, this is the field of power series, so it might be the that might be the Laurent series. And once again, things are happening. Okay. Now, our second thing, if I can get my phone to stand up. The second is we're going to let Q be the field of rational numbers, and we're going to choose a prime number P. For any element A, any rational A, for rational A non-zero, we can write A as R over S, or alternatively as P to the N times R prime over S prime. Where R prime and S prime are integers co-prime to P, I believe, is the idea here. So P does not divide R prime or S prime. And then the valuation V of our rational A being equal to this N is called the p-adic valuation, which is what I was alluding to earlier again. The p-adic valuation of A. Then Q itself, the rationals themselves are not complete under the rationals, but we can just take their completion. So the p-adic completion of the rationals is denoted as our double stroke Q sub P, and it's called this is our field of p-adic numbers. And we're going to note that AN goes to 0 in the p-adic sense if and only if each AN is divisible by a power of P. We'll say P of H, P to the H sub N, where Hn goes to infinity. Alright, so brings us to our next definition. We're going to let K be a field with valuation. It's kind of messy here. With a valuation of V. We're going to set A sub n to be the set of X in K, where with a valuation being non-negative, which is called, this is a ring, and it's the ring of the valuation V. An example, let K be the p-adic numbers let V be the p-adic valuation. Then A of this valuation, why did I write N up there? It's supposed to be A sub V, where V is your valuation. For the p-adic numbers, the ring of our p-adic valuation is just the ring of p-adic integers, which we may have seen written like that. That's what I drew up above for p being equal to 3. Now, if A is a real number greater than 0, or it can be a real non-negative number, then I of alpha being the set of x in AV with a valuation of at least alpha, I prime alpha, these may be some familiar constructions to you. For x, this is x in A of V. For V of x strictly greater than alpha, these are ideals of AV. In particular, if alpha is 0, then I believe I0 is just, I0 is just our AV. But we have that I prime of 0, we're going to set it equal to, we're going to write it as MV for a reason you'll see in a second. And working through our definition up there is the elements of x in AV with a strictly positive valuation. This is the maximal ideal. This is our maximal ideal of AV with, and then we can build our residue field in the standard way where we'll write a K of V to be AV over MV. It's called, this is the residue field of V. Let's look at some examples. Let K be our, I believe this is the formal Ross series on T, as we saw above. And then our ring of valuation V is going to be the formal power series. Our maximal ideal is going to be generated by T. And our residue field, well, this is the formal power series, but we're modding out our determinant. So we just recover our base field, which is very complex numbers in this case. Here, we're going to let K be the p-adic numbers. Then our valuation ring is going to be the p-adic integers. Our maximal ideal is going to be generated by p, so this is going to be p times zp, component wise of course, is that multiplication. And then our residue field, AV divided by MV, is going to be the finite field of p elements, which we recall is z over pz. Alright, so let's move on to another theorem here. So we're going to let x to its absolute value be an ultrametric absolute value on the rationals. Then then the absolute value is trivial, which means we recall it is 1 for all non-zero numbers, or is the p-adic value for some p. Now let's look at the proof. Okay, suppose we have a rational number with its absolute value being strictly between 0 and 1. So this is in the non-trivial case. Then there exists a prime number p such that it has a valuation that is not 1. So p is strictly between 0 and 1. I mean the valuation, not p itself. That wouldn't make sense. We notice that if our n, we notice that the valuation of integers is then at most going to be 1. Now we're going to let n be an integer with its greatest common divisor, with p being 1. Then there exists a and b integers such that a times n plus b times p is equal to 1. So if the absolute value of n is less than 1, then the absolute value of a times n is less than 1. But we know that the absolute value of p is less than 1. So the absolute value of bp is less than 1. I'll make this a new sentence. I think it'll make a bit more sense to parse. So in this case, the norm, the absolute value of 1 would be less than 1, which is a contradiction. So the absolute value of n must be 1. Now we're going to take a to be the absolute value of p, and r to be p to the p valuation of r times n over n prime where n and n prime in integers are co-prime to p. Then the absolute value of r is a to the p-valuation of r. And we're done. And this comes with an immediate corollary. Well, not, maybe it's not immediate, but it's a direct corollary. If K is a complete field with respect to an absolute value, ultrametric absolute value. So, ultrametric absolute value, and the characteristic of our field K is 0. Then K contains Q with the discrete topology, or K contains the p-adic rationals. For our absolute value. Yeah, I think we're a little under time, but our next section is probably going to be a mess here. Yeah, I'm going to have to bisect. I think the next chapter might have to bisect in a weird place anyways, so I don't know. Today's recording's sort of messy, so we're just gonna call it here. Thanks for watching. Sorry this video is a little shorter than usual, but it's a warm up, you know? It's nice to start things off with like a lighter session.